Okay, so today we get to start talking about the actual calculus that's hidden inside of some of the pre-cal that you took last year. But this is going to be the first unit that you talk about in your Cal 1 class in high school or college. And depending on your teacher, you know, that's how much depth they're going to go into. My goal here is to give you sort of a cliff notes on limits. Instead of the formal definitions and things, because I really want you to just understand what it is. And today we're going to speak limits from a graphical approach. So we need to start by actually drawing a graph, and then we're going to talk a little bit about the things that you know how to do with a graph, like the one I'm going to show you. And then we'll take it into the calculus. So why don't you scale this one by 6? 1, 2, 3, 4, 5, 6. You know what? I'm going to go out to 7. 1, 2, 3, 4, 5, 6, 7, and maybe go up to 4, as much as you can fit on your page, I guess. We will need a little room on the side to write. Okay, so if this is a general grid, I'm going to create for you a piecewise function, because in the real world, guys, most graphs that you see are not just one parent function. It's usually a situation where you've been studying data over time, and things in business and in life may happen. So you may look at like a startup company, and and initially, before maybe this could represent before the business actually starts their sales, someone started the company with a set amount of money, and maybe it slowly began to fall, okay? And then we get to a point where maybe business starts to take off, okay? Or maybe didn't take off yet. Maybe it sort of flatlines here for a while, okay? Then we invest a little bit more money and we open the door. So we're still starting in the negatives, but maybe the door opens and business is slow for a while, but then starts to increase. And things get good, you know, things get good for a while, and then maybe they stagger for a while, and then maybe they, I don't know, maybe they drop off or something like that. Or maybe, let's see, how do I want to do this? Maybe we close the doors for a while because some sort of like bad thing has happened, and then when we reopen the doors we're losing money, but our sales start to go up again. Okay, I don't know, totally hypothetical. I just made up a random graph with multiple pieces, and do your best to copy the graph that I have here. It doesn't have to hit, you know, the exact slope or the exact points, but all the critical points, you know, your intercepts, your y values here, 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 try to make those the same as mine. Okay, so in pre-cal and algebra 2, you probably talked about parent functions. You may have even tried to write equations to go with this. You may have seen this as some kind of a square root graph that was turned around. That's of course a line. That's a line. Maybe this piece in the middle is some kind of a cubed root graph. Or maybe you saw it as a wave and you tried to do some kind of a sine or cosine in the middle. I don't know, but that's the kind of stuff that we do in algebra and pre-cal. You also probably understand how to dissect a graph and really look at where is this increasing and decreasing. And if you had to, I think that if I said, okay, where is this graph or business increasing, you really could highlight, okay, well, it's increasing there because it's going up the whole time, and it's increasing there, but maybe these other areas would be areas where you are decreasing, okay? Now, I don't want to focus on necessarily talking about all of that in this video. You don't have to highlight that, okay? Don't worry about highlighting that. Let me undo that. But the other thing that you really need to understand is if this graph has a name, like let's say we call this f of x, right? If I were to ask for things like f of negative 4, f of 0, f of 3, and f of 6. Okay, you need to understand how to answer these questions. This just means, what is the function value when x is -4? And you can just look at your picture. When x is -4, the function value appears to be -1-ish, okay? When x is 0, the y is what? So this is debatable. Some people are like, I don't know, it starts and stops in 2 places. Remember that if it's an open circle, you don't really land on it, which means that this is the actual value at -2. F of 3, if you look at the graph, when x is 3, we're crossing through 0. That's our y. And then f of 6, 1, 2, 3, 4, 5, 6, okay, same thing. Is it up here or is it down below? Well, it's going to be up top because that's the solid circle, that's the open circle. This is all old stuff. This is nothing new. Now, where this becomes calculus is when we start to talk about the idea of a limit, okay? What is a limit? Where does a limit exist? Where does a limit not exist? So, for all purposes, graphically, what you want to be thinking is as x is approaching a specific value, as x is approaching a given, I'll say a given value, y is approaching the limit. Now, what makes this different than just saying find the y value? I mean, this sounds like find the y value. Well, the difference is this word approaching. As long as we are trying to get to the same y value from both the left and the right, that's all that it takes to be a limit, okay? And I'm going to write that right here. Approach the same y value from both sides. Meaning from the left and the right. So for instance, let's go right here to 1. And if we look at the picture and we go down where 1 is on the graph, and I kind of put a little point right here, am I trying to get to this blue y value from both the left side and from the right side? Well, yes, I am. My graph is approaching it from both sides, so that means that limit does exist. Now, where does a limit fail to exist? There's actually 3 cases that a limit fails to exist. One is if it breaks this rule. If you approach different values from the left and right. Another case of a limit failing to exist that I did not draw above is if you have a vertical asymptote. Now, I'm not going to write vertical asymptote. What I'm actually going to write is unbounded behavior. Now, unbounded behavior is the technical way of saying that, you know, there's some sort of a vertical asymptote, and so you're approaching like infinity or negative infinity, and it's all weird. Okay. And then the third that is very rare is on a graph that is oscillating. Oscillating means going back and forth. I'm not talking about a sine-cosine wave. I mean, that's a very smooth, defined curve. I'm talking about oscillating that might look like a heartbeat monitor, where your graph is going along and it can't decide in a given area what's happening. You know, it's like jumping all around and it's not really defined. That's what I'm talking about by oscillating behavior. But any other case, you do have a limit. So what we're going to do is talk about the notation now for limits, and then how to actually approach it with the graph above, okay? So, down to this, the notation for limits in general, I'm actually going to write it down here. An overall limit, you would be asked, the limit as x approaches some value, I'm going to call that c, it's going to be a number right there, of the function's name. Now, our function, I don't want to write an equation because it's a piecewise function, but sometimes there's an equation there. But we're just going to call it f of x is equal to L. Like, that is how you do the notation for overall limit. Okay, so I don't know if you want to write that out in a sentence or not, but the way you read it, the limit as x approaches c for f of x is L. Okay, is the limit. Now, right-sided limits and left-sided limits just means that you're only going to look at that y value approaching from one of these two sides. So from the right side, so this is, make sure you're thinking this is from the right, okay? So if you're coming at your angle from the right, you're going to see a little plus sign right here. And hopefully that makes sense. That's the limit from the left, okay? Or from the right. Hopefully that makes sense, because if you're coming from the right, you're from the positive side of the x-axis. The limit from the left would therefore be a minus sign. And maybe we could do the notation something like that. Now, it's important to kind of differentiate these two, because one of the definitions that you're going to see for a limit says if this is equal to this, then this exists, okay? And that may be another thing you want to write on your paper somewhere. If this formula is equal to this formula, then this formula exists or is true, okay? Now I'm going to show you with specific examples from above, okay? Let's go ahead and look at the limit from the left. I said left, but I wrote right, sorry. Let's look at the limit from the right of the picture as x is approaching 3. Okay, now if we go back up and look at x approaching 3, we're going to go to our graph. Here's where x is equal to 3, okay? But I want to look at from the right. So I need to go to the right of this point, which is on this piece of graph, and I need to start approaching my value. Notice the arrows. I'm actually moving towards it this way and asking, what y value is that trying to get to? Well, that is trying to get to 0. So that would be the limit from the right. Now if I look at that same place of 3 and I approach it from the other side now, like from the left, then I go back up to my picture, I put my hand to the left of 3, and I try to approach the x value of 3. And some people, it helps them to draw a diagonal, like dotted line through the x value so that they can really see, is their graph trying to reach the same point. And of course this is also trying to reach 0 from the left. And so, like I was saying a second ago, the definition, one of the definitions of limit, is that if the limit from the right is equal to the limit from the left, then yes, the overall limit does exist. And the way that you would write it is the limit as x approaches 3 without a plus or minus there, just a general 3, is also equal to 0. And I may even put a therefore. 3 dots in a triangle right there actually mean therefore, so those are congruent. That equals that, therefore that is true. Okay, so you can almost read this chart vertically if you like, and think of it as a chart. Okay, now let's do another one from the picture above. Let's look at the limit as x approaches 0 from the right. We will look from the left, and we will try to decide what happens overall. So I'm just kind of filling all these in, then we'll go up to the top and we'll analyze this, okay? But that's what we're doing, the limit from the right, from the left, and then overall. So let's go look at our picture when x is 0. Okay, I'm going to draw that same, like a dotted line almost, through x is 0. Because the idea is that the dotted line is what we're trying to approach, and we just need to go to both sides of that dotted line and see what's happening. So, if I move, I'll use my highlighter on this. Okay, if I want to go from the right, which is what the first one was, from the right, I go to the right of the red line and look at what piece of graph that I'm on. Okay, it's right here, and I'm headed down this way. So my graph is trying to get to whatever that y value is, which it looks like it's a 1, 2, 3, a negative 3. Now I realize there's an open circle at negative 3, But that's okay, guys, because it's a limit. You don't have to land on it. It's what you are approaching. It's what you're trying to get to, okay? So my graph's trying to get to that hole, and that hole is at -3. Now, same thing, we're going to go towards the red dotted line from the left. And when I come from the left side and I'm on my graph, it looks like I'm trying to approach that y value, which that y value is above the other one. It looks like it's at a -2. So I'm going to put a -2 on my chart right there. Now, this is clear evidence and proof of breaking the rule up here. If you're approaching a different value from the left and from the right, then you do not have a limit. The limit fails to exist. And what we typically write here is does not exist. So because these two are not equal, therefore the limit does not exist. So that's kind of how you can think about analyzing limits. Can you look up there and find another place where the limit is not going to exist? Hopefully you see this area as being a sketchy area, and it will be. The limit will not exist. It will from the left and the right. You'll have a number for from the right, a number for from the left, but overall the limit will not exist. There's another place where the limit will not exist that's kind of tricky. It would be right here. A lot of people think that the limit exists because the graph just dies right there. So you're like, oh, well, it dies, so that's got to be the limit where it stops. But this only has a limit from the right. So this would exist. What is that? 1, 2, 3, 4. X is approaching -4 from the right. This definitely exists. And it looks like it's a -1, okay? But there is no limit from the right. And I said from the right, I meant from the left, I'm sorry. There's no limit from the left, guys, because there is nothing over here. There's no graph on the left. So you can't try to even approach that. So endpoints, another thing you might want to write down, be careful with endpoints, because endpoints only have a one-sided limit, not an overall limit, okay? All right, cool. I think that's enough, actually, for you to get to try a lot of limit problems on the practice sheet. The only other thing on the notes guide is about continuity, which I know I've talked to you guys about, but just to sort of clarify things, there's a definition for a graph being continuous that involves limits, and it is this. It is the limit has to exist. So the limit as x approaches c has to exist. And notice it's the overall limit, not just one of the sides, but the overall limit exists. And it has to be that the function value actually exists. So that means there's no hole, there's no asymptote there. So the function value exists. And the third rule is that these two are the same. So not only does the limit have to exist and the function value have to exist, but those two numbers better be the same. And that is the definition for continuity involving limits, okay? And you can still go with the definition I gave you about there's no holes, there's no vertical asymptotes, and there's no jumps or breaks in the graph. And for types of discontinuities, remember we have removable, non-removable, and jump. And a jump would be like what you see on the picture that we did on the other page. It's going to be a gap or a break in the graph, kind of like what was happening at f of 6 and f of 0 on our picture a second ago, all right? Or we should just write x equals 6 and 0. So the way that we would phrase that is that there's a jump discontinuity when x equals 6 and 0. As far as removable, that would be like a piece of graph that has a hole in it, but it still keeps going right there. and the point has been removed. And so there are none of those on the graph that you saw a second ago, but that's what it would look like. It could also look like this. It could be the same thing, but maybe that point actually does exist. It just exists somewhere random. Both of these still count as a removable discontinuity. And a non-removable discontinuity is going to be your vertical asymptote situation. So if you saw something like this, I don't even know what the graph's doing. It really doesn't matter. But if there's some sort of a vertical asymptote, that would be a removable discontinuity in this problem at x equals 2. Okay, so it's whatever it looks like. So keep that in mind. That's another part of your homework. But good luck, guys. Good luck following those piecewise functions, and we will see you in the solution video.